Hello everyone, my name is Umutcan Çabuk. I'm a PhD candidate working in one of the laboratories of ECE at STSU with Professor Öztürk. Per to some feedback from our professors, we have learned that some of our students are struggling with fundamental mathematics required for some of the courses, some of the engineering courses especially. So we decided to give support and supplementary courses, and per decision I will be assisting you with a few courses including trigonometry, basic calculus, and complex numbers. So these are some really hard and abstract topics, but they are very useful in advanced engineering lectures and research. So in order to pass the advanced courses, in order to understand what's happening in the advanced courses, it's necessary to at least get a basic understanding of trigonometry, complex numbers, derivatives, integrals, and some other subjects of mathematics. We will not be going into much detail, but I will tell you the basics. So here you can see my mail address, and if you have any questions, if you want any one-on-one lectures, if you want to discuss some of the topics or want those slides, you can always write me and find me in STSU building, ECA building, per mail. I'll be answering my mails promptly. So for the trigonometry part, we will be discussing trigonometric functions in one course, in one part actually, and in a second part we will be discussing trigonometric equations. What are they, how can they be solved using basic math techniques, and lastly we will be discussing what are the applications of these trigonometric functions and equations, especially in the field of electrical and computer engineering. So mostly in electrical part we will be using them a lot for circuits, for currents, voltage, etc., and also for signals. Let's look at the agenda for this particular presentation. We will be revisiting angles, especially the right angle of a triangle, right triangle, and edge relations according to these angles. We will be revisiting trigonometric functions, some identities of trigonometric functions. I will be presenting some visualizations on graphs, and we will be solving a few examples to make the topic more concrete. As I said before, the topic is very basic, very fundamental, but extremely important to understand very well. Angles are measured in a standard position, as you can see in the demonstration on the left part. So when we measure angles, we always are talking about this standard position. Of course, the angles can be in any format, in any orientation or position, but this is the standard measure. The initial side is the positive x-axis, the horizontal one, which is fixed. The terminal side is the ray in quadrant 2, and what is quadrant 2 will be explained later. And you are free to rotate about the origin. Counterclockwise rotation is positive and clockwise rotation is considered negative. Coterminal angles and are angles that have the same terminal side, so it's 60, 420 degrees and minus 300 degrees are all coterminal, which means they are somehow equivalent, but not exactly the same. In practical, we will see that these angles have too much in common, but not exactly the same. Apart from degrees, we have one more measure for angles, and it is called radians. And let's explain this with an example. If we multiply an angle by pi over 180 degrees, then we will find the radians. Let's look at 60 degrees. If we multiply it with pi over 180 degrees, then we will find pi over 3 as the radian equivalent of that degree. 60 degrees is equal to pi over 3 radians. They are equivalent. And when we mean 60 degrees, we also mean pi over 3 at the same time. And we can also easily convert from radians to degrees when necessary. So when we multiply the angle by 180 degrees over pi, then we will get the degrees. So let's look at pi over 4 as radian units. If you multiply it by 180 degrees over pi, then we will find 45 degrees as a result of this multiplication. And another important part is 360 degrees is 2 pi radians, and this is 1 revolution on the standard position axis. So if you rotate this line on the left top quadrant, which is quadrant 2 in this example, if you rotate it 360 degrees, you will end up with the same position for that line. And the arc length of the imaginary circle that encapsulates this angle can be found as multiplying the central angle with the radius of that imaginary circle. So S, the length of that arc, is theta times r, radius times the angle. Here, please pay attention, the central angle must be in radian measure, so it should be in the pi format, pi over 4, pi over 3, etc. Let's look at right triangle, which has one right angle in one of the edges, one of the corners, sorry. We name these edges of the triangle per 2 angles. So that's not a rule, but you can see that it's done frequently. So the angle in the opposite at the opposite side of that angle A, capital A, is represented with small a here. So, and the other naming is similar. Sinus A, we have quite a few trigonometric functions, but the most popular and the mainly used are sinus, cosinus, tangent, cotangent, secant, and cosecant. So these will be the ones you see frequently. There are other derivatives, but used less frequently. And sinus A is the sinus of angle A, which is the opposite side, length of the opposite side over hypotenuse. And hypotenuse here is obviously C, because it is the opposite angle of the right angle. It's always called hypotenuse. So sinus A, sinus of angle A, is the opposite side, which is small a, over hypotenuse, which is small c. So it's called A over C. This will be the result of our sinus. And cosinus is adjacent side over hypotenuse, which is B over C. And tangent does not include hypotenuse in the calculation. It's the opposite side over the adjacent side, which is A over B. These calculations are only for the angle A, because these functions, just for an example, are fed by A as the input. So if you have the input A for cosecant, then it will be C over A, because it's defined as hypotenuse or over opposite. Secant of A is hypotenuse over adjacent, which is C over B. And finally, cotangent of A is adjacent over opposite, and it translates as B over A. So it is normally, I do not advise memorizing anything, but it's very, very useful to keep these definitions in mind. There are some special right triangles with ratios and numbers that are easier to remember. Not every triangle provides these numbers, so it changes from one triangle to another, but there are some special ones that you should be familiar with. 30, 60, 90 triangle and 45, 45, 90 triangle are two of those. And let's see the cosinus 30. It is obviously square root of 3 over 2, and which is also the equivalent of cosinus 60, because please look at the definition here. Sinus is opposite over hypotenuse and cosinus is adjacent over hypotenuse. So one angle sinus would be the cosinus of the other angle. And sinus 30 is 1 over 2, and tangent 30 is square root 3 over 3. So, and please stop here and calculate secant and cosecant and cotangent of these angles as in practice. And as you see, cosinus 60 is 1 over 2, just exactly same as sinus 30, and sinus 60 is the same as cosinus 30, which is square root 3 over 2, and tangent 60 is square root 3. Why? Because it is, let's look at the definition, it is opposite over adjacent. So let's look at the opposite of tangent 60, which is square root 3, and the adjacent is 1, so the division yields square root 3 only. And same rules apply for the 45, 45, 90 triangle, but as you can see, these three edges are exactly same just because of these angles, and it is proved with these trigonometric functions. Cosinus 45 is square root 2 over 2, sinus 45 is exactly the same, and tangent 45 is, as you can see, it's only 1, because the edges are identical. When it comes to identities, there are quite a few in trigonometry. Tangent A is identical to sinus A over cosinus A, because when you see here, actually let's go back, sinus is opposite over hypotenuse and cosinus is adjacent over hypotenuse. Let's look at the tangent. It's opposite over adjacent, so hypotenuses won't be included in calculation of tangent just because of this ratio, this division. When you divide A over C to B over C, then you won't get C in the answer, so it will only depend on A and B. So this is why tangent A is equivalent of dividing sinus A with cosinus A. And it will be exactly the opposite for cotangent. Cotangent A will be cosinus A over sinus A. By the way, cosinus minus A, which is, let's say if A is the angle of 30 degrees, minus A is angle of minus 30 degrees, which will be equivalent to 330 degrees, considering the shape given in the top left part here. And cosinus minus A is equivalent to cosinus A, But it's not true for sinus function. Sinus minus a is equivalent to minus sinus a. So it's better to keep these ones in mind. They are not exactly equivalent. And tangent minus a is just like sinus. It's minus tangent a. On the other hand, secant minus a is just like cosinus. The minus sign disappears. It's secant a. Cosecant minus a is minus cosecant a, and cotangent minus a is minus cotangent a. So it's better to keep these ones in mind. If you cannot, I understand that it's not easy to memorize these stuff. You can just think that they might not be straightforward, and please think about them. Please try to calculate, and if you still cannot do the calculation or memorize, please keep in mind that these are quite tricky, and look for a source like an online source or your notes or a wiki page. So please keep in that mind, these are quite tricky, but it's always better if you can memorize the whole stuff. By definition, cosecant a is 1 over sinus a, and secant a is 1 over cosinus a. So these are mostly done by definition. Cotangent a is 1 over tangent a, which its name also suggests that. Sinus a is 1 over cosecant a. These ones are derived from these equations easily. So you can just change the places, replace cosecant a with sinus a using basic algebra, and you will get these results. Cosinus a is 1 over secant a, and tangent a is 1 over cotangent a. What's much more important is Pythagorean identities. Sinus square a plus cosinus square a is always 1, and this is used a lot in more advanced topics of trigonometry, and even in engineering applications of trigonometry you will be using this a lot. So please keep this in mind, and it is a very helpful, very easy to keep in mind, and very, very useful in advanced topics. Tangent square a plus 1 is secant a, and 1 plus cotangent square a is cosecant of a, and a is any arbitrary angle. Let's look at an example to make this stuff more concrete. We have a triangle with one right angle on the right side, and we have one known angle of 30 degrees. And let's calculate the trigonometric functions, and you are free to stop the video here and make the calculations yourself. Sinus 30 by definition will be the opposite side over hypotenuse, so it will be 1 over 2, which is quite basic and straightforward. Tangent 30 will be opposite side over adjacent side, which is 1 over square root 3, and which is also equivalent to square 3 over 3 if you multiply the bottom part with square root 3. Second of that same angle will be hypotenuse over adjacent side, which will be 2 over square root 3, and this is equivalent to 2 times square root 3 over 3. Cosinus 30, on the other hand, is adjacent side over hypotenuse, which will be square root 3 over 2, and cotangent 30 will be just square root 3. And finally, cosecant 30 will be hypotenuse over opposite side, which is 2 over 1, which is 2. It's very straightforward. Let's look at another example where the right angle stands on the right side, and we have a known angle of 60 degrees. Sinus 60 will be exactly the same as cosinus 30. Yes, you guessed it right. Cosine 30 is square root 3 over 2, and we will get square 3 over 2 again. Tangent 60 is opposite side over adjacent side, which is square root 3. Secant 60 is hypotenuse over adjacent side, which is 2. Cosinus 60 is adjacent side over hypotenuse, which is 1 over 2. And cotangent 60 is adjacent side over opposite sides, which yields square root 3 over 3. Finally, cosecant 60 is 2 over square root 3. We have another example, but I will not go through it, so you are free to stop the video here again and solve the problem. Or if you understand the topic very well, if you memorize the stuff, you can skip this example. Here we do not know the angle, but instead we know length of two of the edges. One hypotenuse, which is 1, and one opposite side of an arbitrary theta, which is 0.25. So what we should do here, writing the equations while writing the functions again, and filling from reverse. Here are the results. I will not read every single step here, but please try to solve if you are struggling with this relations and functions. And of course, you will need Pythagorean theorem to find the length of the third side here. What if we get secant of theta as 4, and let's try to find the values of other trigonometric functions of that theta. Let's look at a more advanced example. It's a little bit more complicated, but still easy in its sense. So we have sinus of an angle theta, which is 0.25. And the question asks cosinus of that theta, tangent of that theta, and secant of that theta angle. Now, we do not know the exact length of the edges of a triangle, but we know the ratios. And sinus theta is the opposite side over 1. So we know the ratio. Let's draw a triangle with an arbitrary angle theta and then right angle. The hypotenuse will be length of 1, and the opposite side will be of length 0.25, but it doesn't have to be like that. It should be 10 for the hypotenuse and 0.5 for the opposite side. So we all know the ratio between these edges, but not exact numbers. And for the third side, we have to use the Pythagorean theorem to solve the equations. The Pythagorean theorem was, let's look at a few slides before. The Pythagorean theorem is sine squared of angle A plus sine squared of angle A is 1. So we will use this information. And when we apply the cosinus function to that theta, we will get let's look at a more complicated example. It looks like it's complicated actually, but it's not. It's as easy as the previous one. In this example, we have sinus of an angle theta, which is defined as 0.25, and the question asks cosinus, tangent, and secant of the same angle theta. So here we do not know, and we cannot know the exact lengths of the edges, but we know the proportion between these edges. Let's draw an example triangle. We have one right angle and we have one angle theta. We know the sinus. Sinus means the opposite side over hypotenuse. So it could be 0.25 over 1, it could be 2.5 over 10, etc., etc. We know the ratio, but we don't know the exact length. It's not necessary for this calculation. Here, in order to calculate the third side, the unknown side, we should use the Pythagorean theorem, and we have to get squares of these edges, and we have to add them 0.25 square, the square of the unknown side will be equal to 1. So if you make this calculation with your calculator or mobile phone, you will get the length of the exact length of the unknown side, and it will be let's look at a more advanced example. Given secant of an arbitrary angle theta is 4. Find the values of the other 5 trigonometric functions of that particular angle theta. Okay, it may seem hard, but it's actually not. Here we do not know the exact length of the edges, but we know the proportion, we know the ratio between them. Please remember that secant was Let's look at a more advanced example. It may seem more complicated, but actually it is not. Given secant of an angle theta is 4, find the values of the other 5 trigonometric functions of a theta. Okay, what we know is the ratio between the edges, not the exact lengths. But this is still enough to solve the other trigonometric functions. We do not need exact lengths of a triangle. If you just know the ratios between the edge lengths, that's totally fine. And secant is hypotenuse over adjacent side. So if we know secant is 4 for an angle theta, we know that hypotenuse would be 4 and adjacent would be 1. So the ratio is 4. And they could also be 40 over 10, but it doesn't make any sense. It doesn't make any difference. For the sake of simplicity, let's use 4 and 1. So we get the triangle as you see. We have one right angle, one angle theta, one edge with size 1 and one hypotenuse with size 4. Now it's easier to calculate the other functions. And it's also possible to use Pythagorean theorem to calculate the unknown edge. As you may recall, square of hypotenuse would be sum of squares of each edges. So 16 would be equal to square of 1, which is 1, plus square of length of unknown edge. And this edge, length of this edge turned out to be square root of 15. And now we can proceed to the trigonometric functions of theta. And sine of theta would be square root 15 over 4, and cosinus theta would be 1 over 4. Cosecant theta would be 1 over sinus theta, which is 4 over square root 15. And secant theta would be 4 again. Tangent theta would be opposite side over adjacent side, which is square root 15 over 1. And cotangent theta is 1 over square root 15. We have one more example. Now we have given a sinus theta 0.25, and the question asks for cosinus, tangent, and secant of that angle. If we draw the triangle, we have one right angle, we have one named angle called theta, and we know the proportion between the opposite side of that angle and the hypotenuse, which is 0.25. We can use the Pythagorean theorem to solve the third side, and let's revisit the quadrant scale and see which trigonometric functions yield positive or negative results in which parts of that quadrant. In the first quadrant, the top right part of the scale, we have all the functions positive. Every single trigonometric function here yields a positive result, which is greater than 0. Let's revisit the quadrant scale and see when these trigonometric functions produce positive results and when they yield negative ones. In the first quadrant, where an arbitrary angle A is between 0 degrees and 90 degrees, all 6 trigonometric functions we have learned are positive, always. The result is always greater than 0 if the angle is greater than 0 but smaller than 90. In the second quadrant, where the angle is between 90 degrees and 180 degrees, we only have sinus and cosecant as positive, and the rest of the functions always yield negative results. In the third quadrant, where the angle is between 180 degrees to 270 degrees, we have cosinus negative, sinus also negative, tangent and cotangent positive. In the fourth and last quadrant, where the angle A is between 270 degrees to 260 degrees, we have cosinus and secant positive and rest negative. So there is a simple mnemonic to memorize this called all students take calculus, and these capital letters stand for the ones which are positive. It's not 100% accurate, but it's still good to memorize which functions are positive. So in the first quadrant, all of them are positive. In the second one, sinus is positive, plus we have cosecant positive. So it's going like that. In quadrant 1, the theta is always its original reference. So 60 degrees is equivalent to 60 degrees. So this is the most basic representation. But in the second quadrant, 60 degrees, from time to time, dealing with larger angles can be hard when it comes to calculations. So we can use reference angles for larger angles which map that large angle to its equivalent in the quadrant 1. So it's we can reduce and find an equivalent of a large angle in quadrant 1, which will help us during calculations. And theta prime is always equal to theta in quadrant 1 because it's the simple small angle we use. In quadrant 2, we are dealing angles between 90 degrees and 180 degrees, but we can reduce that angle into quadrant 1 equivalent by subtracting that theta from 180, and when we are working with radians as the angle unit, then we can subtract theta from pi and find the quadrant 1 equivalent of that quadrant 2 angle. And let me give an example. If you are working with theta which is 120 degrees, then sinus 120 degrees would be equivalent to 60 degrees according to that calculation. And if you try that, you will see the results will be the same for all trigonometric functions if you correctly convert the angle. For the third quadrant, we can get the equivalent reference angle by subtracting 180 from theta and pi from theta if you are working on radians. For the last and fourth quadrant, we can find theta prime as 360 minus theta, or 2 pi minus theta. To better represent, understand, to better represent, understand, and prove things related to trigonometry, we use a special circle called unit circle. its radius is always 1, and it is this one. So I will be using this slide and the previous one together. I will be making back and forth. So this circle has radius 1. You can see here on x-axis it's called 1, 0, and here you can also see on y-axis it's also length of 1. Here the x is the cosinus of theta, and theta is an imaginary angle. You can think of it here, and we will be extended it until from 0 until 360 degrees, which are both equal in this scale. And for cosinus theta, the smallest number would be -1, and the largest number would be +1, and the variable y would be sinus theta, and its values are also ranging from -1 to +1. And the Pythagorean theorem is easily observable on this unit circle here, and x squared plus y squared would always be 1. And from here we can prove that cosinus square of any angle theta plus sinus square of that angle theta would also be 1. And the points where sinus theta values are 0 here in this unit circle are NP, where n is an arbitrary whole number like 1, 2, 3, etc. And the points here where the cosinus of angle theta are 0 can be obtained from pi over 2 plus m pi as a degree. So when you can formulate your angle theta as pi over 2 plus mp, or in other words 90 degrees plus n times 180 degrees, where n is a whole number, then you will end up with cosinus of that angle theta as 0. It's always fun to play with this unit circle. And let's look at some graphs, some visualizations of sinus and cosinus functions. Let's assume a function f which gets x as its input. A times sinus bx minus c plus d would be that function. And let's assume another function gx equals to a times cosinus bx minus c plus d. The fundamental period of sinus and cosinus is always 2 pi, as also explained in its unit circle, which is equivalent to 360 degrees. And the domain of sinus and cosinus functions would be the field of real numbers. And the range of these functions would be from minus a to d. In order to understand what these trigonometric functions mean in the real world, in some engineering applications, we have to use visualizations of them. Let's assume two functions, fx and gx. Fx would be a times sinus bx minus c as the angle plus d, and g of x is a times cosinus bx minus c as the angle plus d. So fundamental period of sinus and cosinus is always 2 pi, which translates as 360 degrees, as we can see in this unit circle. The angles and the trigonometric functions of these angles start to repeat themselves in every 360 degrees. So the period of these functions are 360 degrees. 60 degrees here is quite equivalent to 360 plus 60 degrees when it comes to trigonometric functions. And for sinus and cosinus, it's not different. So the period is 2 pi. The domain, which means the output result of these functions, sinus and cosinus functions, are in the real numbers domain. And when looking at these functions of fx and gx, the range of the output would be from minus a plus d to a plus d, where a is encapsulated in the absolute value function. And a here in absolute form, without using its minus sign if it is negative, is the amplitude of this function. And d is the vertical shift of the result. And the period of the graph is 2 pi over b, since we have a multiplicator called b in the angle. And the phase shift, or so-called horizontal shift, is c over b. And using these relations, we can draw nice illustrations of these functions. Here in the top left part, we have y equals to sinus x, the basic sinus function. You can see the amplitude here in the vertical axis, and you can also easily realize the period of one full cycle of sinuses. In the second one, we have y equals to 3 times sinus x. Here you can see that the only thing changed is the amplitude in the vertical axis, in the y-axis. So the period of sinus did not change. Here in the top right chart, you can see that we still have the same sinus function, but shifted towards the positive y-axis. So it's the same wave, but just over the ground. But when we change here the angle, like B or C, we will be seeing changes in the frequency, or let's say period of the wave here. Y equals to sinus 3x gives us a more dense, a more frequent wave here. In the same period of time, if we assume x-axis is time, then we have much more ups and downs here. So the frequency and the period have changed. And y equals to sinus x minus 3 gives another different chart. Here let's look at the formula of the functions, and c here causes a horizontal shift. So our chart is quite shifted, and we can just play with this outlook of the sinus function by changing the parameters like amplitude and frequency, etc. The same also applies for the cosinus graphs. We can shift it, we can tilt it, we can change the frequency or change the amplitude without touching the frequency at all. So it just depends on the parameters given here. A is the amplitude, and B is here a parameter affecting the angle and the frequency. C over B is the horizontal shift, and D is the vertical shift. So the maximum a cosinus function, a maximum value of the cosinus function would be 1, and A times 1 would be a, and if we calculate d plus d, we get a plus d as the maximum possible result. So it always depends on d. For tangent and cotangent, we have a similar logic, but the domain of tangent is quite different. It's an x, so that x is not equal to pi over 2 plus n pi, where n is a whole number. And domain of cotangent is also quite different. X, so that x cannot be n times pi, where n is another whole number. And range of tangent and cotangent are R, which is the real numbers domain, just same as sinus and cosinus. But the period of tangent and cotangent is pi over b, and these are the graphs of secant and cosecant. We still have a few more topics to be covered within this module, but it could be easier if we stop here and continue the rest in the next session. Hello everyone, we are now about to start the second session of our trigonometric functions short course. So far we have seen some trigonometric functions including sinus, cosinus, tangent, and a few more. And now we will see the inverse variations of these functions. These functions appear to be one-way functions, but they are actually not. So when we know an angle, we can calculate its sinus, cosinus, tangent values. But likewise, if we have these proportional values, we can find the angles that yield these values. So let's take sinus as an example. If we know the angle is x, an arbitrary angle, we can calculate sinus x. And it will be a ratio, just like 1 or 1 over 2 or square root 3 over 2. And similarly, if we have that proportion, say 1 over 2, then we can calculate the angle that gives that proportion when applied to sinus function, or similarly for cosinus function. And this inverse function of sinus is called arcsinus, and the input here is not an angle. Input for the sinus function is an angle, and the output is a ratio. But in contrast, for arcsinus function, we feed the function with that ratio, and in result we get the angle as the output. So it's just the other way. Here the input domain is very limited, because output of sinus function can be any number between -1 and +1. So this is the reason why the input of arcsinus can be between -1 and 1. And as the output, we will get an angle which is between -pi over 2 to +pi over 2. And if the result is between 0 and 1, then the solution must be in quadrant 1 and 2. Otherwise, if the y value, the result, is between -1 and 0, then the solution is, the angle I mean, is in either quadrant 3 or quadrant 4 in the standard position. In a very similar way, we can calculate the inverse of cosinus, which is called arc cosinus or arc cosine, or even shorter, you can call arc cos. And we can calculate inverse of tangent, which is arctangent. In arctangent, the domain is, the input is all real numbers, and the range is again minus pi over 2 to pi over 2. In cosinus, the range is quite different. Range is from 0 to pi, which means from 0 to 180 degrees. Let's take a look at a few useful trigonometric identities. If we know sinus of some angle A and sinus of some angle B, we can find sinus A plus B or A minus B using the sinus and cosinus values of angles A and B. We can not simply add or subtract these sinus values, but there is a formula for that. So sinus A plus B is simply sinus A times cosinus B plus cosinus A times sinus B. So just pay attention to the change in the angles. And if you want to subtract B from A, the plus sign in the middle would be minus and the rest will be the same. Likewise, we have another formula for cosinus A plus B. In that one, cosinus A times cosinus B minus sinus A times sinus B will give us cosinus A plus B. So just pay attention to the reversal of the signs in the middle of the terms here. When adding in cosinus, we are just subtracting in the formula, and it's vice versa. Cosinus A minus B will be cosinus A times cosinus B plus sinus A times sinus B. And another formula is coming for tangent also. Tangent A plus B is tangent A plus tangent B over 1 minus tangent A and tangent B. And again, pay attention to the signs. These formulas are very, very handy when solving equations and problems. And we can, using the same principles as before, we can simply calculate double of some known angle. So if we know sinus 30, using sinus 30, we can calculate sinus 60. Here in the previous formula, we have something broader. For example, if we know sinus 45 degrees and sinus 30 degrees, we could calculate sinus 15 using the sinus subtraction formula on the top line. Here we can simplify these formulas to get the doubles. Sinus 2a, where a is an arbitrary angle, is 2 times sinus A times cosinus A. And cosinus 2A is cosinus square A minus sinus square A, which is also equivalent to 1 minus 2 sinus square A, and which is also equivalent to 2 times cosinus square A minus 1. And tangent 2A is simply 2 tangent A over 1 minus tangent square A. And the formula is derived from the broader formula I showed in the previous slide here. Similarly, we can calculate the half angles. If we know, let's say, sinus 60, we can easily calculate sinus 30. So yeah, 60 and 30 are pretty popular ones, and you may already memorize them, but you can calculate every single angle using these formulas. For example, if you know sinus 45 degrees, you can easily calculate sinus 22.5 degrees, which is not that common, so it's not easy to memorize it. And sinus A over 2 is plus or minus square root of 1 minus cosinus A over 2. And the sine here is determined by the quadrant of A over 2. So it depends on where your angle stands in the standard position. Cosinus half A is plus or minus square root 1 plus cosinus A over 2, and tangent A over 2 is plus or minus square root 1 minus cosinus A over 1 plus cosinus A. So again, the sine here is dependent on the quadrant of the input angle. We still have some more handy formulas. Let's think about any triangle. It doesn't have to be a right triangle. It can be any arbitrary triangle that is properly a triangle. We have a law called law of sines, or in the long form, law of sinuses. In every triangle, sinus of an angle A over its opposite edge, small a, equals to sinus B over the opposite edge B, and it's also equal to sinus C over small c, the opposite edge. And also the small a, as you see, name of the edge, opposite side of angle A, capital A, over sinus A equals to B over sinus capital B, which is equivalent to C over sinus capital C. These equations can be used to solve a lot of problems, especially when the subject triangle is not a right triangle with one angle of 90 degrees. These can be applied to any triangles. And we have a cosinus counterpart for these series of laws. It's called law of cosines, and it's like with the same naming system. C square is a square plus b square minus 2a times b times cosinus capital C. Capital C is here again the angle in the opposite side of edge C. Similarly, b square is a square plus c square minus 2ac cosinus b, and a square is b square plus c square minus 2 times bc cosinus a. Let's look at vectors. Vectors are very important in many engineering applications, including electrical circuits and radio waves, electromagnetism, and so on. A vector is an object that has a magnitude and a direction. Given 2 points in Cartesian coordinates P1 called x1, y1 and P2 called x2, y2 on the plane, a vector v that connects the points from P1 to P2 is v equals to x2 minus x1 times I plus y2 minus y1 times j. Here I and j are not the I and j from complex numbers, but they are the unit vectors of length just 1. Now I is the unit vector in the x direction, and j is the unit vector in the y direction when you think about Cartesian coordinates of 2 dimensions. And the unit vector in the direction of v is v over norm of v, or let's say absolute value of v. A vector v can be represented in the component form by v equals to vxi. Here vx is the x-axis component of v, plus vyj. And the magnitude of v is square root of vx square plus vy square. And using the angle that the vector makes with x-axis in the standard position as we show before, and the vector's magnitude, the component form can be written as v equals to magnitude of v times cosinus theta I plus magnitude of v times sinus theta g. So this is where exactly the trigonometric functions take place. We write vectors using these trigonometric functions. And let's look at the vector operations. We can do a scalar multiplication. A vector can be multiplied by any scalar or a number, a real number, a whole number, etc. Let's look at this example. Let v be 5i plus 4j and key equals to 7. Then key times v equals to 7 times 5i plus 4j, and we can distribute 7 inside in the parentheses and we get 25i plus 28j as a result. So we just multiplied the vector with a scalar number. We can do dot products. It is multiplication of two vectors. And let v be vxi plus vyj and w equals to wxi plus wyj. So v times w could be vx times wx plus vy times wy. The result is a scalar. The result of the dot product is not a vector. Let's look at another example. Let v be 5i plus 4j and w be minus 2i plus 3j. And v dot product w would be 5 times minus 2 plus 4 times 3, and the result would be 2. We have another solution for the dot product. It's another formula that gives the same result. V dot product w could also be written as magnitude of v times magnitude of w times cosinus theta. And here the theta is the angle between these two vectors of v and w, as in this little picture here. And two vectors v and w are orthogonal, which is also called as perpendicular, if and only if v dot product w is only 0. So if their dot product, if any two vectors dot product equals to 0, then these are orthogonal. We can also add and subtract vectors to or from each other. And this is done by adding and subtracting same components only. So i's must be added to i's and j's must be added to j's. Let v be 5i plus 4j again, and w be minus 2i plus 3j again. In that case, v plus w could be 5i plus 4j plus minus 2i plus 3j, and the result would be 3i plus 7j. And on the other hand, 3v minus 2w could be defined as 3 times 5i plus 4j minus 2 times minus 2i plus 3j, and the result would be 19i plus 6j if you continue the equations. And we can also calculate the magnitude of this vector, and it could be roughly 20. And this was all for this lesson, and we will continue more advanced topics on trigonometric equations in the later parts. Thank you for watching and listening.